Good morning, good afternoon, everyone. My name is Mike Clark. We'll give it a second or two for everyone to log on and transition into the webinar. And we have a quick poll up here right now while we're waiting for a couple of seconds, so feel free to answer the poll, and then we'll get started here shortly.
Oh, it says I don't get to vote. That's not fair.
Oh, I was hoping if we got any more than one vote, I was going to say, huh. We'll give it another couple of seconds here. All right, thank you for those who voted. And Paul, the results, I'm not sure if you can see them on the screen or not, but 60% of the folks said they have a good awareness, and 40% said that they do index maintenance on a schedule.
Cool.
And thankfully, no one said they were Paul Randall.
That's what I was going to vote, but I couldn't.
Yeah, and folks, in case you didn't know it, today we have Paul Randall with us. He is going to be talking about index fragmentations, internals, analysis, and solutions, and anything else that comes to his mind. Again, my name is Mike Clark. I wanted to say thank you to our sponsors, HVR Software, as well as AWS. These seminars are really good, and they're a great way to disseminate information and to partner up with like-minded individuals. But there is an overhead and cost, and we are thankful to HVR and AWS for partnering with us and coming alongside and helping us and providing an ability for us to do these webinars. We appreciate that very much. Do a little bit of housekeeping here. So Past Summit is the granddaddy of all of the training for SQL Server. And so this year there's a little bit change in the venue as well as time. For the past several years, 5 or 6, it's been up in Seattle. This year it's going to be in Houston. It's going to be the November 10th to the 13th. There's still early bird pricing to February 28th of this month. So not February 29th this year, but February 28th. So you can get your discount there. There's actually good material at the past website if you wanted to have some information to share with your boss on the ROI, the good benefit of going to a conference such as this. They may say, wow, that's a fair bit of money, but there's quite a bit of collateral on the site, the past.org website, to help you with that discussion with your bosses. Feel free to go visit that. I've used that a couple of times when it's been a challenge. This database administration group is just one of many groups that past virtual groups have out there. There's language groups, there's other technology groups, there's security, there's a women in technology, even DevOps. We all know about that. Many of us have come from that environment. We're recovering, but no, if you have any of these topics are near and dear to you, if you go to past.org and click on virtual groups, you can register and be on their mailing list and attend sessions with that kind of event and so forth. Another thing that the past organization does is they also have SQL Saturdays. It's basically an all-day event on a Saturday. They're free of charge. They are being held around the world, and right now there's quite a few coming up here in the USA and Canada. For those of you that are out of the country in APAC, there's one in Wellington. I believe that's New Zealand. Edinburgh, Italy, Belgium. Man, they're all over the place. So if you're anywhere near those locations, go to SQLSaturday.org and register for that particular session. They'd love to have you. In the past organizations, we tried to do very quickly is, it's a great community. There's plenty of ways to connect and learn and share information and even ask questions for the community. Yesterday during our stand-up at our little company, we actually posted some questions out to the community real time and got answers right back while we were still discussing the issue. So it's a very useful community. So feel free to join up to that. Everything is free. And today, as we mentioned earlier, we do have Paul Randall with us. He's going to be talking about index fragmentation. And there's a lot of words on the screen right now about Paul, and most of us probably know about him, but I'm going to turn it over to Paul directly to give him as much time as possible because he has more information to share than time probably would allow us. So, Paul, I'm going to make you presenter.
All right, thanks, Mike. And just before we get started, I'll send a PDF of the slides and a zip file of the demos you're going to be doing to Mike, and he can post them up wherever on the PASS website. And we'll stop every so often for questions, and Michael will interrupt me if there's any questions that are pertinent to what I'm talking about. Anyway, index fragmentation, internals, analysis, and solutions. I have a few little housekeeping slides as well. Just a very quick slide about us, SQL Skills. There's the other people that work for SQL Skills. We do training, consulting, blah, 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 blah. We have a bunch of classes coming up in Chicago in May, everything from performance tuning through accidental DBA, Azure, Power BI, and so on. And you can find all the information there on our website. The links are on that slide. Mike mentioned the PASS Summit in November. If you can't make it to the PASS Summit, maybe you can't travel, for instance, outside Europe, there is a conference coming up in March and April called SQL Bits. And I'll be there, Kimberly will be there, and Erin will also be there. And we're all doing pre-con sessions, and we're all doing regular sessions as well. So if you're interested in SQL Bits, go to sqlbits.com. And also, right after SQL Bits, we have our little show that we do twice a year, and the spring show is coming up in Orlando, and we have a whole bunch of people speaking there, lots of people from Microsoft, and again, lots of post-con, pre-con sessions, and we'll be there, lots of fun. If you've never tried Pluralsight, there's a bunch of recorded courses. We have 65 recorded courses up on Pluralsight, and you are welcome to try it out completely for free. Shoot me an email just saying Pluralsight code, and I'll send you back a 30-day trial code. All kinds of cool, interesting stuff to watch. And finally, me. So I'm Paul. I used to work for the SQL team. I wrote a bunch of the code in the storage engine, blah, 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 blah. The really interesting stuff on that slide is how to contact me. So there's my blog link down at the bottom, lots and lots of stuff from my blog. I think there's more than 1,000 blog posts down there. I'm on Twitter at Paul Randall, and if you have any questions about what you see me talking about, or if you're watching this offline or after the fact and you have a question about something that I've said in the presentation, please shoot me an email. Just make sure you say question about PASS presentation in your subject line, because I get lots and lots of emails, and I like to make sure that I prioritize random questions from the community from people that have actually watched something that I've been talking about. So paul@sqlskills.com if you want to contact me. So the technical stuff. You cannot escape index fragmentation, because as soon as you have any indexes, especially non-clustered indexes, that don't match your insert pattern, you're going to start to have random inserts, and random inserts, as we are going to see, cause fragmentation. Now, fragmentation itself is not the only problem. People think, okay, fragmentation slows down scans, and yes, it can do. That may or may not be a problem for you. But there's also, how did we get to the fragmentation in the first place? And the fragmentation slows down scans is not the only kind of fragmentation, but that's what most people think about. One of the things that really bugs me is over the last, 5-10 years, as IO subsystems have got faster and faster and faster, people have started to say, oh, you don't have to care about fragmentation because you've got really fast hardware. It doesn't matter. And that is not true. It may be true that fragmentation on your particular system isn't an issue, but you can't just put your head in the sand and completely ignore it. You have to at least evaluate whether fragmentation is causing you a problem or not before you decide to completely discount it. So what we're going to cover over the next 60, 75 minutes, depending on questions, is data access methods. How does SQL Server actually make use of index structures? We'll talk about the various different kinds of fragmentation. We'll talk about how fragmentation happens, and we'll talk about how you can detect fragmentation, how you can mitigate it, and how you can remove it if you do have fragmentation. So a very basic look at an index structure. And it doesn't really matter whether we're talking about clustered indexes or non-clustered indexes. Oh, by the way, we're talking about row store indexes here. We're not talking about column store at all. So a row store, non-clustered or clustered index has the same basic structure. Down at the bottom, those pages marked with L, that is the leaf level of your index. If it's a clustered index, then they're going to be data pages, and that is your actual table. If it's a non-clustered index, then those are index pages, and the records in them are an awful lot smaller. It's just what you've defined in the index, maybe any included columns, and a backlink back to the matching data record that has all the other columns. Now you can see that there's a series of black arrows down there at the leaf level, and these are a doubly linked list. So the storage engine can do an ordered scan in ascending order, assuming you have an ascending key, or descending order. Now up here, and there's a level which I call the parent level, and this is the level above the leaf level. And in these pages here, and there could be multiple of these levels, in these pages here, you can see that these little red arrows coming down. This is because the records at this level have what's the lowest key that can appear on the page I'm linking to, and a page pointer. So for instance, maybe let's say in this very simplistic view of an index, there's two records. And the first one says, what's the lowest key that can possibly appear on this page here? And it'll actually be a null value, which stands in for kind of negative infinity. And then a pointer to that actual page. And then there'll be, what's the lowest key value that can appear on this page? And then a pointer down to here. And this is how SQL Server navigates down from the root page, the very first page at the top of the B-tree structure, figuring out which way through the index to go to get to a particular record using all these linkages. And there's a doubly linked list at every level of the index. Okay, so very basic index structure. So there are different ways that SQL Server can make use of this structure. The first one is looking up a single record. So this kind of nothingness up here, this is metadata. So the metadata for the index has the page ID of the root page of the index, and every access to an index starts at the root page. So it goes to the root page and it knows what key value it's looking for, and it decides using these index records which way to navigate down through the B tree. So it goes down to the next level, figures out which way to navigate through the B tree, goes down to the leaf level and finds the particular record that matches the search argument or the index key that you're looking for. Now, at every level of the index, right, there is some cost. So it has to spend some CPU cycles figuring out which record has the key value or the key range, if we're at the non-leaf levels of the index, that's going to have the key value that we're interested in. And it does what's called a binary search over the records in the page, because the records are accessible in index key order. Okay? They don't have to be stored physically in order, but they are accessible on the page by SQL Server in index key order. So it can do a binary search to figure out which record it needs to look at. And that's more efficient than just taking, for instance, a page with 100 records on and reading them all in order. It's going to be, on average, more efficient to do that binary search than to do a brute force, read all the records until you come to the one. So it pays to have your index to be as short as possible, short in terms of the number of levels. Okay, if you have a very, very large index key, then you can have only a few records at each of these pages, and so there's going to have to be lots and lots and lots of levels. This is called the fan out of the index. Lots and lots and lots of levels to store all the linkages and the how to navigate through the B-tree stuff. And so you have, for every record that you're looking for, you have more binary searches because you have more levels to traverse. So keeping your index keys as small as possible can help you with performance. And you might say, well, we're only talking about a few microseconds. Sure, but if you have thousands of requests every second for index lookups, then those microseconds all add up. Okay. So anyway, that's a single record seek. A multi-record seek, or a scan. So this is where you've given a range for your search predicates. And you might say, just show me everything where salary greater than 50,000. That's still you giving a range because there's an implied and less than infinity on the other side. Okay. So what SQL Server does is it does essentially a single record seek to get to the first matching record in the index. And then it gives it back to the query processor. The storage engine does this and gives it back to the query processor. The interface between the storage engine and the query processor is one record at a time. So it gives the record back to the query processor and it remembers where it was on that page. So the query processor does its thing and then says to the storage engine, hey, get me the next record. So the storage engine knows that it's doing a scan, so it just goes to the next record on the page. Now there's some safeguards built in that, for instance, if somebody changes this page that the storage engine is positioned on while the storage engine was waiting for the query processor to say, hey, get me the next record, the storage engine has to restart up here to find the next record that matches. But if this page doesn't change, it doesn't have to go navigate all the way through the B tree again. So it's a kind of efficiency mechanism. So it carries on giving records back and so on and so on and so on until it gives the last record back on the page. The query processor says, get next record. The storage engine says, oh, there's no more records. So it goes up to the page header. And the page header is a 96-byte area that has a bunch of information about the page. And one of the bits of information is a pointer to the page that has the next set of key values on. Okay. It has to be a pointer because there's no guarantee that this page that has the next set of key values from this one is physically adjacent to it in the file. Right? So it goes and looks in the buffer pool and says, is this page in memory? If the answer is yes, that's called a logical I/O. We like that because then the thread bumps back out of the buffer pool and carries on scanning. If this page that we're after is not in memory, then that thread that's doing the scan has to issue a physical read, and it has to stop and it has to wait until that physical read completes. Okay. Anyway, at some point, either immediately or after the read completes, this page will be in memory. And so we carry on, storage engine carries on giving records back to the query processor. Oh, next page, records back, next page, until it finds a record that doesn't match our search predicates, okay, or predicates. And that is doing a multi-record seek or a scan. Now, I didn't quite tell you the whole story there, because when I said here, oh, we go and we look and see in the buffer pool if that page is there, and if it's not there, we have to issue a physical read, and then we have to wait. It would be really cool if, when the thread goes and looks in the buffer pool, that page is always there, right? And that is done by a mechanism called read ahead. As we have a thread that's scanning through these pages down here, right, it's also looking at these pages up here. Now, remember I explained the level above the leaf level in an index, what I call the parent level, has essentially a list of all of the page IDs in key order, because that's what an index does. So by looking at this level and seeing what page IDs this page points down to, the read ahead mechanism can drive pre-reading these pages into memory ahead of the scan point, so that when the thread goes to the buffer pool and says, hey, is this page in memory? The answer comes back, yes. So it's a logical I/O, it completes immediately, and the thread carries on scanning. There's no waiting that has to happen. So by reading these pages ahead, hence the name read ahead, SQL Server can do more efficient scans because the threads don't have to wait. Okay? And it does that by this mechanism here. Now, a few things about read ahead. There is a feedback mechanism, okay? So it knows where the scan point is, and it basically won't read any more than 1,000 pages ahead of the scan point. So it's not going to read in your 1,000,000-page index if it only needs to scan 10 pages. Okay? And it can issue various sizes of IOs, okay, from a single page read up to a multiple, very large multi-page read, a 4 megabyte read in 2016 plus over 8 parallel IOs. And this is because it's more efficient to do larger reads. Consider the case of when you want to read 8 pages, 8 contiguous pages. It's more efficient to do one trip down the IO stack asking for a 64K read than 8 trips down and up the IO stack, each asking for an 8K read. And there's an issue, which is, if we go back to this, imagine that this is like several thousand pages. As the read ahead is building up its list of pages to read, if it comes across pages that are out of order, and I'll define that in a minute, it has to use smaller IOs. Out of order means the next logical page that has the next set of key values on is not the next physically contiguous page. Okay? So when you have these pages that are out of order, that causes read ahead to issue smaller IOs, which means that read ahead is less efficient, which means that your scan is less efficient. And when these pages are out of order, that's called fragmentation. Hence the understanding that most people have, which is fragmentation slows down scans. Okay? So that, to be more specific, is what's called logical fragmentation. Okay? And there are various other names that people have invented to come up with to describe the kinds of fragmentation and so on. I like to use what's in books online because I actually wrote the books online for fragmentation way back in the mist of time. So logical fragmentation is where the next logical page, the page at the leaf level of an index that has the next set of keys on it, is not the next physically contiguous page. And when that happens, that page is out of order. And so read ahead has to do smaller IOs. So you've got more IOs happening when you have more fragmentation for the pages that you're scanning. And that means you're not getting the best performance for your scans. That may be absolutely no problem to your system at all. You might never ever do scans, in which case this kind of fragmentation is not going to hurt you whatsoever. Right? You still have to analyze your system to see whether that kind of fragmentation does hurt you or not. Now, The effect of this kind of fragmentation is not going to be really noticeable for very small indexes. Okay, especially if you've got the indexes entirely in memory, then it's not going to be a problem at all. And for small indexes, what do I mean by that? Well, back in, say, 2000, 2005, I would have said, maybe 1,000 pages. Nowadays, I might increase that, depending on the speed of your I/O subsystem, to a few thousand pages. You're probably not going to worry about fragmentation for those small indexes. And this kind of guidance, I came up with this guidance when I was at Microsoft because people wanted some guidance. And based on experience working with clients and so on, Microsoft clients and product support, this was the guidance that I came up with. And also it's from, I used to sit on some of the old Usenet news groups. And some of you are probably young enough that you don't even remember Usenet, precursor to forums and so on. And I'd be sitting on one of the SQL Server news groups at lunchtime, helping answer questions, and somebody would post a question like, hey, I've just rebuilt my index and I still have 45% fragmentation. What do I do? Help. And I'd reply saying, how many pages does your index have? And they'd come back and say something like 13. And I'd be like, dude, it doesn't matter. Okay, that kind of small index fragmentation is not going to cause you a problem at all. Take a chill pill. Anyway, though, for larger indexes, it might be a problem. Okay, but the index fragmentation affects scan performance, kind of what people understand about fragmentation. There is so much more to it than just that. And of course, you can get the reading of how fragmented your index is from the average fragmentation in percent in the DMV. How are we doing? Any questions, Mike?
Yep, I have one. I was just coming off mute, so that was perfect timing. So the question is, and you might get to this, how do you detect if this fragmentation is hurting you or not? Size is one thing, right? But how do you know if it is or not? Yep.
We are going to get to that in a nutshell. So I'm going to tell you how you can detect the various forms of fragmentation. So what you're going to do to figure out whether fragmentation is an issue, let's say you've got a very large index and you find out that it's like 90% fragmented. The workload that's using that index, you do some performance analysis on it, see how long your average queries are taking, then remove the fragmentation and see if the queries speed up. And if you want that speed up to be there all the time, you're going to have to do periodic fragmentation removal and maybe mitigate fragmentation from happening with index fill factors that we're going to talk about. So it's very simply, basically, does your workload speed up when you remove fragmentation or stop fragmentation happening? And if that is the case and you want it to always be at that speed, you're going to have to do something about fragmentation. If you don't care about the effect of the fragmentation, or you remove the fragmentation and it has no effect whatsoever because you're, for instance, not doing scans and your entire database is already in memory, then you don't have to do anything about it if you don't want to. Okay, there's nothing that says thou must do fragmentation removal all the time. Okay, but you can't just say, oh, fast hardware, don't care, because even with fast hardware, you can still make a difference and it can still cause you problems. Okay. Any other questions, Mike?
That's it for now. Well, the one just came in. Seems a quick review. What is a binary search again?
A binary search is, imagine that you had a list in order of, say, 100 numbers, and you want to find a particular number. A binary search says, go to slot number 50. Is that the number you want? Let's say no. Is the number you want above that or below that? Let's say it's larger than that. So now you've got another range. You've split the range in two, hence binary. So you've now got from the 50th position to the 100th position. So you go to position 75. Is that the one we want? Let's say no. So now it's above. You go to element 87, and so on and so on and so on. And so on average, the number of elements that you have to look at to find a particular value in that list of 100 ordered elements is lower than just reading through the entire list until you find the element that you're looking for. And that is the classical definition of a binary search. It's a very simple computer science algorithm.
Perfect. Thank you.
Okay. So here's the other kind of fragmentation that many people don't think about. And this is what I call page density. And page density means you've got wasted space on the pages or empty space on the page. As we're going to see, when fragmentation occurs, it generally creates pages that have a large amount of wasted space. So let's say you have a bunch of pages that are only 50% full. That means that to store the rows on your pages, you're taking essentially twice the number of pages. Now, this is an example. This is not how fragmentation works all the time. You're not, just because you've got fragmentation, I'm not saying your indexes are twice the size. They're going to be larger, okay? Which means that it's going to take more disk space. which means you're going to have to do more IOs to read the same amount of data in, because the data density on the pages, the use of the space on the pages is suboptimal. Okay. If you've got a bunch of low page density pages, that means you're taking up more space in the buffer pool to store those pages. And memory on your system is one of the most precious resources. So even if you have no scans at all that are not affected by fragmentation, you might be taking up more space in your indexes because of fragmentation, and that's causing your workload's kind of working set of data to not be able to be held in the buffer pool. So fragmentation, in this sense, page density, could be causing your workload to do more IOs, or to do IOs when it doesn't have to, because you might be able to get rid of fragmentation and so essentially make your indexes smaller, and now your entire workload fits in your buffer pool and you never have to do physical page reads. That's going to speed up your workload. But if you think about just fragmentation affects scans, you're never going to think about that particular knock-on effect of fragmentation. So this is the other kind of fragmentation that I want you to be aware of, wasted space, and there's nothing you can do in hardware in the IO subsystem that fixes this, because the page is 8K, and if it's only 50% used, it still takes up 8K on disk. It still takes up 8K in the buffer pool, right? And you can get an idea of what kind of wasted space you've got from the DMV, again, average page space used in percent. So there's a blog post there, a little link that I did a few years ago, where I put out some code using a DMV, sys.dmos buffer descriptors. And this DMV returns a row for every page that's in the buffer pool. And the script that is on that blog post there might take a long time to run. It might take a few hours to run if you've got a very large buffer pool with lots of stuff in it. Don't think it's going to cause you a problem. You could kind of think of what this DMV is doing as a no-lock scan of the metadata that's in the buffer pool. So that DMV running for a couple of hours on your buffer pool is not going to cause you any performance issues. Now, this was a survey that I did. So I got a lot of information back from 900 servers across the world, people like you listening in, kind of totally random, about how much buffer pool space is used. Okay, so not the size of the buffer pool, but how much is being used to store pages. And out of that use, how much is empty space? Because the buffer pool keeps track in real time of how much empty space there is on every page that's stored in memory. And so there's a very interesting set of data here. So we have on the x-axis, this is the logarithmic scale in terms of gigabytes of space in use. So we're going up to what, about 256 gigabytes here. And then over here, we have percentage of that space that is empty. Okay. There's some interesting data points. So first off, I could draw a red line at 30% all the way across and say probably those people under the 30% line are just mitigating index fragmentation. And I'll explain what I mean by that in a few more slides. Mitigating index fragmentation by proactively leaving space on pages to prevent fragmentation from occurring. Okay, give me a few more slides and I'll explain what that is. Now, here's some interesting outliers. So this is probably about 200 gigabytes of in-use space, but more than 60% of the pages of the page space being used there is empty. So this could be a system where there's an awful lot of IO happening because maybe the workload doesn't fit in the 200 gigabytes of buffer pool memory, and so it's having to continually push stuff out of memory and read more stuff in because those pages don't have very much data density. Some more cases over here. So these are small buffer pools, like 10 gigabytes, so maybe these are small VMs or something. More than 90% of the page space being used is empty. That's a very, very poor use of memory. Now, again, I'm not saying that this is going to affect you. It could be that all of your workload is in memory and you've got a bunch of this fragmentation, and then you don't care, right? Because if you're not doing scans and everything's in memory, fragmentation isn't hurting you, potentially. There's one more thing we have to think about. But this is something that you at least need to look at to see whether it's the case. So if you have a system where, if you look at weight statistics, you're seeing page IO latch share weights are very high on your system, That means SQL Server is having to drive a whole bunch of page reads of stuff that's not in the buffer pool. And you've got to think, why is it doing that? Why isn't that stuff in the buffer pool? And it could be that your buffer pool just isn't big enough. It could also be that you've got a fragmentation problem across the instance that you don't know about. And so you're wasting a bunch of your buffer pool space. And removing that or mitigating that fragmentation means more stuff can be stored in memory, means your workload goes faster because it's not having to do so many physical IOs. So that's an entirely different way of looking at fragmentation that's got nothing to do with range scans. Okay? How much buffer pool space is being wasted, and can you make your instance faster by stopping that happening? Any questions before we go into page splits?
No, not yet, but there's a question here. How do you determine the proper fill factor? But I think you'll get to that.
Yep, I'm gonna talk about that. I will tell you the magic number that that everybody should be using, and the magic formula that everybody should be using in a few more slides. So fragmentation happens because, so we've now talked about data access methods. We've talked about the two different kinds of fragmentation. Now let's talk about how does fragmentation happen. And it's an operation called a page split. Okay? This occurs when SQL Server needs to put a record in a particular page at the leaf level of the index because of its key value. Okay? When you do an insert and into an index, there is no choice where the record can go. It has to adhere to the key ordering. And so if there's not enough space on that page where that record has to go, the page has to split. In other words, SQL Server has to make some space to insert the record. Generally, what it's going to do is what I call a 50-50 split. It's going to split in the middle of the page. And I'm going to show you some examples of page splits when we do our first demo. I've only got a few little demos because it's hard to do really interesting demos about fragmentation. But I will demo this for you. So the other things that could cause a page split is a record that's already on a page needs to get bigger. So maybe you've got a variable length column and you update that column to be larger and there isn't enough space on the page. It's going to have to do a page split. Now, when I say there isn't enough space on the page, the very first thing that SQL Server will do when it needs some space on a page is it will look in the page header and say how much free space is there, because that is tracked in real time. Let's say we need 100 bytes on the page. And there are 110 free bytes on the page, but they're not contiguous, they're not one chunk, okay? Because there could be records that have been deleted, and then new records come in that don't quite fill up all the space that was used before, and so you've got little chunks of free space scattered through the page. What SQL Server will do instead of a page split is it will do a in-memory compaction of the page. It will basically spin up an empty copy of the page, take all the existing records on the page and insert them into the new page, making the contiguous free space available for the operation that needs it. And then it will just log the image of the new page. That's an awful lot more efficient than logging a page split, as we're going to see. So it could be a new record, it could be an updated record, it could be because you're using snapshot isolation. Snapshot isolation, when you turn it on, either read committed snapshot isolation or just regular snapshot isolation, as soon as you turn it on, it doesn't matter whether you've got any queries using snapshot isolation, any change to a record requires that the record has a 14-byte tag added on the end, which basically has a little timestamp of when this record was created and a pointer to the previous version of the record that's stored in the version store in tempdb. So suddenly the record is growing by 14 bytes. If there isn't enough space, a page split has to occur. So just turning on snapshot isolation can cause page splits, which can start to cause you potential performance issues from the two kinds of fragmentation that I've showed you. And there's another case, which is if you have an availability group readable secondary. On the secondary, under the covers, any isolation level that you specify gets turned into snapshot isolation. So that means that those records on the readable secondary have to have version tags, 14-byte version tags added on the end. But the readable secondary has to be the same at the byte level as the primary database. So as soon as you have a readable secondary over on the primary database, it starts making sure that all changes to records in that primary database cause an extra 14 bytes of free space to be added on the record, and that is logged so that on the readable secondary, there is 14 bytes of free space to enable versioning to work on the readable secondary. In a nutshell, this means that when you turn on a readable secondary, you might start to get page splits happening on your primary database in indexes where it wasn't happening before. and that might cause you a performance issue. Okay. And note all the way through this, I'm not saying it will cause you an issue, I'm saying it might. You have to evaluate whether fragmentation causes you a problem or not. Okay. So, various different things that can cause page splits to occur. Now, a page split is actually very, very expensive. So imagine we have this very simple, very small kind of index here with 3 pages at the leaf level and 1 root page up here, very, very tiny index. And they're all completely full, or A, B, and C are completely full. Somebody comes along and wants to insert a record, and the record, the key value says it has to go on page B. There isn't enough space on page B, so we have to do a page split. So what happens is another page is created out of thin air. Okay, I'm calling it down here B1, and the page B1 is going to go here logically in between B and C, because what the split's going to do is take a bunch of records from the end of page B and move them into this new record, this new page, sorry, that's been inserted in between B and C, thus preserving the linkages in key order. Okay, so now we've got half the records that used to be on B. On page B1 down here, we've got the second half of the records on page B. And then we have to fix up the B tree. Page B used to point at page C as the one that has the next set of records. That's no longer the case. It has to point to page B1. So B's page header has to be updated to point to B1, and B1 points back at B. C used to point back at B as the previous page of records, but that's no longer the case. So C's page header has to be updated to point back to B1. So that's fixed up the doubly linked list at the leaf level of the index. But then page B1, the new page, has to be reachable from an index traversal, from the root page. And so in the level above the leaf level, a new record has to be inserted on this page that points down at this one that says, this record is going to say what's the lowest key value that can happen here, and a pointer. Okay. And so this page has been updated. This page has been created and a bunch of records put on it. This page's page header has been updated. This page has a new record on it, and so the page header gets updated as well with the new record count. And this is all fully logged, no matter what recovery model you are using. Okay, so everything is fully logged. This is done by a thing called a system transaction, which is a sub-transaction of your transaction. Whether you started one or not, you have a transaction because SQL Server starts one for you. And that system transaction commits, and it commits irrevocably. It can never be rolled back. So if, let's say you did begin tran, insert record into B, it caused the page split, it did the insert, and then you said roll back. The only thing that gets rolled back is the insert into this page. This entire page split remains forever. Okay. Now, as I said, it's fully logged, and it logs copying these records over. So it can be a lot of logging, and that's expensive. And if you have SSDs and you say, oh, I don't care about the extra reads because of read ahead during my scans, you're already having a performance problem just getting to the fragmentation itself, because page splits generate a lot of transaction log, and that's an issue. You're generating more log, and all that log has to be backed up and restored, and log shifts and sent across the wire to your availability groups, database mirror if you have one, and so on and so on and so on, right? SSDs don't stop page splits from happening. SSDs don't stop wasted buffer pool memory from having fragmentation. Okay? So don't just stick your head in the sand and say, oh, I've got a fast system, I don't have to care. You do. You at least have to evaluate. Now, unfortunately, there's no really good way to track page splits happening in real time. What I've just told you, I call nasty page splits that cause a problem. There's also, unfortunately, good page splits. Now, imagine that you have an ascending key index, and let's say you've got an int identity column as the first key in your clustered index key. So that means that every insert is going to happen essentially on the right-hand side of your index, if you think about looking at an index in front of you. So it's going to be taking a page on the right-hand side of the index and inserting new records into it. It's going to fill up the page. Then it's going to have to go and create another one. Unfortunately, the storage engine calls that add another page on the right-hand side of an append-only insert pattern a page split. And none of the methods of tracking page splits differentiate between them. Okay? There's a perfmon counter, page splits per second, in the access methods performance object. That doesn't differentiate between them. There's a column called leaf count in the DMV, DMDB index operational stats, which tracks page splits. That does not differentiate. There's even an extended event called page split that does not differentiate between good and nasty page splits. The only way to use that extended event is to take the page ID that says it just got split and have a look to see whether it was a nasty page split or a good page split. However, there is one foolproof way to do it. Okay, so there is a log record, and in that little blog post link there, it says what this log record is. It's called an LOP delete split. That's the name of the log record. And that is only ever generated by a nasty page split. So you can use, there's an extended event called transaction log. And the transaction log extended event fires whenever a log record is generated. So you could have an extended event session if you wanted to track in real time page splits happening, looking for log records named LOP delete split, and then getting some more information and figuring out which index it is. And that's very cool. And my blog post links to a blog post of Jonathan's that shows you how to do that using extended events. If you don't want to do that, you can also use a log scanner. So there's an undocumented command called fn_dblog, fn_dblog, that's been around since at least 7.0. And that allows you to look inside the transaction log. And my blog post there has a little script that will look for those particular log records being generated and tell you which indexes they are from. There's even better. If you don't want to have that running in real time on your system, you can take a backup, take it to another system, and there's an fn dump dblog, which looks through the log that's stored in a backup. So you can actually do some processing on the log backups to look and see how much LOP delete splits are being generated. That's if you want to track it in real time. You could also just use the DMV I'm going to show you, because that's also going to show you that you've got fragmentation, and you can infer from that you've had page splits happening. So let me show you a little demo to show you how expensive page splits are. Any questions so far, Mike?
Yeah, here, let me get to it. Well, you're kind of covering the last one here, good page splits versus bad page splits. But one is somewhere in here, what is the effect of compression on any of this, if any?
It's really orthogonal, I would say, meaning it doesn't really have any effect, because all compression does is means the records that you're storing on the pages are smaller. You're still it's still prone to having fragmentation issues. You've just got smaller records. Okay, so I would say compression doesn't help or hinder fragmentation. Anything else?
No, that's it.
Okay, cool. All right, let's have a little demo. So a script to show you how expensive page splits can be in terms of extra logging. And I'm running all these demos on 2019. And for the longest time, I still have a Windows 7 laptop, because Windows 7 is very stable, but my presentation laptop since last year is now Windows 10, so that I can run 2017 natively without having to mess around with virtual machines. So anyway, 2019. But everything I'm going to show you works, all these scripts work all the way back to 2005, except the next demo we're going to do, where I'm going to use a little bit of extended events, and that will only work from 2008 onwards. But none of you should be running production or playing around with 2005 unless you've got an application that forces you to, because they haven't upgraded. But none of you should be playing with 2005. You should all be on like 2012 or higher. So this is everything I'm going to show you is going to work on 2012 and higher for sure. Anyway, I'm going to create a little database called page split test, and I'm going to create a table in that database that has what I call big rows. So I'm simulating roughly 1,000 byte rows. It's going to be bigger than that, obviously, because I've got a little bit of overhead in the rows, but bear with me, roughly 1,000 byte rows. And then I'm going to create a scenario where there's enough space on this page to insert one record without causing a page split. And we're going to have a look and see how much transaction log is generated. And then the next insert we do is going to cause a page split, and we can see how much more expensive the insert is when a page split occurs. So I'm going to begin a transaction and do the insert. Then I'm going to use this DMV tran database transactions scoped down to my page split database, and we'll see how much transaction log was generated by that little insert. And 1,256 bytes. when you're running these demos on, say, earlier versions of SQL Server, you will see slightly smaller numbers because log records get slightly bigger and bigger in all versions of SQL Server as they add more potential fields. But we're really looking at the ratio of non-split insert compared to split insert. So that was 1,256 bytes. So this one here is going to cause a page split. 7,380 bytes to do that insert, exactly the same size record. So that's roughly 5 or 6 times more transaction log when that page split occurs for those roughly 1,000 byte records. So now let's go down to roughly 10 byte records, like so. And if any of you are wondering how I get this highlighting to happen and how I get it to reflect what I did in the results, look on Google or Bing and look for me and how to configure SSMS for presenting. And that shows you all the little things to tweak to make it show up nicely like this when you're doing demos.
I'm glad you said that because I was just drooling over this.
Yeah. Yep. And it's in all versions of Management Studio. I'm running not quite the very latest, but I think it is 18 or 19, whatever the latest version as of a month ago was. You could also do these demos in Azure Data Studio. I just find Management Studio is easier for me to present on because I'm just so used to it. But I also do stuff in Azure Data Studio as well. Anyway, so did we run that? And this is really useful because if I get a question or something when I'm teaching and I don't know what I've run, I can go and look and it shows me what I just did, so I don't accidentally try and do something twice or mess up my demo. Anyway, so we're going to create another scenario here, enough space for 1 insert but not for 2. So these are roughly 10 byte rows. So if we look at the non-page split insert, 356 bytes. The page split insert, 6,572. So that's what, 17, 18 times more transaction log for that insert to happen when a page split occurs. So you can see that as the row size gets smaller, the kind of multiplication factor of how much extra log is generated for a page split gets larger and larger and larger. So now let's go and do small rows. And what I'm doing here is I'm causing SQL Server to not do a 50-50 page split. So around page splits, SQL Server is actually not very smart. Most of the time, it's just going to do a 50-50 page split. But sometimes if it determines that there are 2 big distinct ranges on a page, it will do what I call a skewed page split. So in this case, it's actually going to split in between these 2 ranges rather than splitting halfway through the page. Now, I said that SQL Server wasn't very smart. Imagine that you have a page, an index page that has several hundred small rows on, and you come in to insert an 8,000 byte record, and it has to go on that page. You would think that SQL Server is smart enough to say, I need 8,000 bytes. I will do a single page split that gives me 8,000 bytes of free space. Nope. What it will do is a 50-50 page split. And now you've got 2 pages with 4,000 bytes of free space. So it picks one of those and splits it again. Now you've got a 4,000 byte and 2,000 byte free space, and so on and so on and so on until it's done about 7 page splits. And the very last page split creates a page that has enough space for 8,000 bytes. So it might be that you get multiple page splits occurring because of one insert rather than just a single page split. Anyway, I digress. Did I run that? Yes, I did. So let's create this extra scenario here. And then without a page split, 268 bytes. And you can see there's a lot of overhead for a log record because I'm inserting a row that's 15 bytes or so, and it has all this extra overhead. And then for a page split, so we had 368 bytes versus skewed page split, almost 11,000 bytes. So that's 45 times more transaction log. So, and that's the end of the demo. So if you think about it, if you're having lots of page splits, the smaller your records are, the more extra log you're generating. And if you're doing lots and lots and lots of page splits, that's lots and lots and lots of extra log that's being generated, sent across the wire, backed up, restored, scanned by replication, and so on and so on. And so just because you've got fragmentation means you've been having page splits. And that could be causing you a performance issue, not just in your workload, but also in all those ancillary things that are happening, scanning and log backups and so on, that you don't realize. And so mitigating that can just do a general speed up of all of those different things. So any
Paul?
questions on the demo?
Yeah.
Oh, yes, one.
So on this page splits impacting log file, how does that impact, say, recovery or startup if you had a crash? Restore?
So it's not really going to impact recovery if you have a crash, because it's a very small transaction. So it's not like it's a very long running, very large transaction that's going to take a long time during recovery. So I would say it's not going to really have any effect on crash recovery. It's more the effect it's going to have on things that have to consume that log outside of recovery. So log backups, they're going to be bigger, take longer to restore because there's more log to be restored. More log that you're sending over to your availability group, so that might slow down your availability group operations and so on like that. Okay.
Is there a way to see if that would that just be in the AG log? Is there a way to that would just be measured in like latency?
Yes, just the amount of log that's being sent over, and it could also, because there's more log that has to be processed on the readable secondaries, it could also be that your readable secondaries are behind the primary, and the further behind the readable any secondary, the further behind the secondaries are, potentially the longer it's going to take for the secondary to come online if it's picked as the failover partner or set as the failover partner. Because you might have a synchronous availability group, that doesn't mean that the synchronous replica is up to date with the primary. All it means is that when a transaction commits on the primary, all of that transaction log is in the log on the replica. The replica still has to be doing redo and redo and redo and redo forever. And if there's more log, that could take longer for it to do the redo. So, make sense?
Yep.
Okay. All right, back to the slides. So we could summarize our causes of fragmentation being basically page splits. Okay? You could also think of low page density being caused by table or index schemas that have very large records. For instance, let's say you have a 5,000 byte table row, and that means your clustered index data pages can only store one of those rows per page. So that means there's 3,000 bytes being wasted on every page. That is low page density, which I consider a kind of fragmentation, but that isn't caused by page splits. But pages being out of order and low page density are one of the things that are caused by page splits. And so that page splits could be because of a random key. So maybe developers chosen a GUID as the high order key. And as we're going to see, having a random GUID as the cluster key can even affect non-clustered indexes. I'll show you that in the next demo. The updates to variable length columns using snapshot isolation, using a readable secondary, or not using a fill factor. And fill factor, we've mentioned a couple of times now, is the way that you can mitigate fragmentation. And it says down at the bottom there that even deletes can cause fragmentation by lowering page density. This is the case where you've got an append-only insert pattern. So maybe you've got an int identity column. The new records that get inserted in that table or index will always be conceptually on the right-hand side. So if you have a workload that goes back and deletes records in the earlier pages in your clustered index, say, that space that's freed up by deleting those records earlier than the insert point is never going to be used by inserts, because those inserts are happening on the right-hand side of the index. So in that case, you might have a large clustered index that you're deleting from over time that gets fragmented in terms of low page density. And so that could be causing more pages to be used in memory, and it doesn't fit in memory anymore, so it's driving more IOs, and doing a rebuild or a reorganize of that index every so often to kind of reclaim, if you will, that deleted space can bring the page density back up to full again on those earlier pages and alleviate a performance issue that you might be suffering. And again, remember, I'm saying might and maybe, not will be. Okay? Something that you have to evaluate. Fill factor. So If you can't change all your index keys, because it's very hard to go and change index keys, and you can't really set your non-clustered indexes to all have the same keys as the clustered index, say, because that defeats the purpose of having indexes supporting different search patterns. So as soon as you have non-clustered indexes that don't match your insert pattern, they're going to be having page splits because you've got random inserts happening. Or if you have a cluster key that's random, you're going to be having page splits that are happening, right? So what you can do is you can tell the storage engine, I would like to leave some free space on the page when the index is built or rebuilt to allow random inserts to happen or random row expansions to happen without causing a page split. And so you pick a number, and that number determines how much free space is left on the pages when the index is built or rebuilt. So you are proactively causing lower page density to avoid page splits happening. Okay. Now, don't do this for the entire instance. Okay. If you set the fill factor for the entire instance, all of your indexes will use that fill factor unless you specifically override it. It is way better to leave the SP configure option to 100%, don't leave any free space, and only specify a fill factor for those indexes that need it. Otherwise, if you specify a fill factor at the instance level, and you've got some large indexes that don't need that, you have to go and set the fill factor for those indexes back to 100. And it's kind of a backwards way of doing it. Leave the instance alone and only specify fill factors for those indexes that really need it. Now, some of you may be saying, oh, Paul, the SharePoint maintenance white paper says set the SP configure option to 80. Why are you saying something different? I'm saying something different because the SharePoint maintenance white paper is assuming that there isn't a DBA, a competent DBA, looking after the SharePoint instance of SQL Server. And so by having a fill factor in there, that's better than not. Also, if you've ever looked at SharePoint, you'll see that they choose a random GUID for most of their clustered index IDs. And so you get horrible fragmentation issues happening with SharePoint systems. Right? But for you guys as DBAs, or if you're a developer looking after a SQL Server, leave the instance fill factor alone and only set the fill factor for those indexes that really need it. Now, if you don't have a problem with an index, leave the fill factor at 100. Okay? And there's a little note there saying that fill factor of 0 is the same as 100. And I actually had to put a little slug into Books Online for 2000 and 2005 there, because there was a lot of confusion about whether 0 and 100 were actually different. They're not, they're exactly the same. But for a system or an index that has fragmentation issues that you want to mitigate, what number do you use? And the magic answer is, there isn't a magic answer. Okay. Unfortunately, I was just teasing you all. There is no magic number that you can put into production that's going to work for everybody in the world. And there's no formula. If there was, I would tell you about it. What you need to do is, if you know that you've got a particular index where removing or stopping fragmentation gives you a performance boost, pick a fill factor, put that fill factor into production, monitor the fragmentation with that fill factor in there. And maybe you might need to tweak the fill factor up or down a little bit, or maybe tweak how often you rebuild or reorganize the indexes to put that free space back. And the number that most people start with is 70%, maybe 70% or 80%. And that means for 70%, leave 30% of free space on the pages. And many people in the world just put 70% for those indexes that have a problem and walk away and never do anything else. And that might be totally fine. And that's why, if you remember the graph I had, the scatter plot from how much free space is in the buffer pools on those servers, I said I could draw a line at 30% and say those people are probably just implementing a fill factor. And they've got lots of index pages with less than 30% free space. Right? So if you have an issue, you pick a fill factor, put it in production, monitor it, and maybe tweak something about that. It's that simple. Right? So having a fill factor is going to allow that index page to have some extra space taken up by new inserts or expanded records without causing a page split. So it's kind of putting off the point at which a page split occurs. Eventually, though, that page is probably going to fill up and a page split will happen. And your trick is getting to that index in your index maintenance and resetting the free space so that page splits don't happen, or you don't have lots and lots of page splits happening. Okay. Now you can find out what's going on in terms of fragmentation using this DMV, DMDB index physical stats. And it's a DMV that we came up with in SQL Server 2005 as a replacement for the old DBCC show config that I wrote for SQL 2000. And of course, DMVs are really cool compared to some of the old DBCC commands, because with DBCC show config, you'd have to use the insert exec trick into a temporary table to be able to do any post-processing of the results of show config. But the DMV is what's called composable. You can just select whatever you want from it, do where clauses and all kinds of good stuff. There are 3 modes to the DMV. The first one is the limited mode, and I'll come back to this slide in a second. So this is what the limited mode does in the DMV. It makes use of the same trick that read ahead does. It does not read the leaf level. It doesn't have to, because the limited mode just tells you how many leaf level pages you have and what kind of logical fragmentation there is. And it can do that by reading the level above. Right? So by reading this level above, right, it allows, because it has a list of all these page IDs in order, it can determine the fragmentation. And this was what I put into DBCC show config for 2000, where I called it very imaginatively with fast. Okay, not a very cool name, but that's what the with fast option did that I built for show config in 2000. It used the level above to figure out what the fragmentation is. So this is what the limited mode does in the DMV. And for many people, this is going to be fine. Just use the limited mode. Right? If you want to know what's going on in terms of page density, you have to read the leaf level. And so detailed will do a limited mode scan to find the logical fragmentation, and then it'll read every page at the leaf level and figure out a whole bunch of other stuff, right? Including, for our purposes in this lecture, the amount of free space. If you have an incredibly large index, you could use sampled. What sampled will do is a limited mode scan first to find the logical fragmentation, and then it will read every 100th page. So it's not statistically valid, it's just doing every 100th page, and then it'll figure out for that 1% of the leaf level pages and multiply by 100, essentially, and that gives you a sampling of the detailed mode. Right? Now you might say, well, I don't want to run this at all on my production system because it's going to drive a whole bunch more reads. Cool, then what you can do is you can take your backup that you've done, you can restore it on another system, okay? Create a linked server from your production system, go over to the linked server with a restored copy of your production database, run the DMV over there on the restored copy, because it's exactly the same as the production copy. And then you can take the results of that run of the DMV on the linked server, bring it back to production, and if necessary, do any kind of index maintenance on the prod copy of your database. So you can offload that. And also, as a side effect of offloading that, if you're doing a kind of backup copy restore to a different system, you can also offload your CheckDB to that secondary copy as well. And that will tell you if, at the time the backup was taken, there were no corruptions in your production database. We did this slide already. So there's a lot of stuff in the DMV. And what you really need to look for what we're talking about here is the average fragmentation in percent, which if you have an index that has problems, you want that to be low. And then the average page space used in percent, you want that to be as near to fill factor as possible, and how many pages. And that's really what you need to look at. There's all kinds of other things that exist in the DMV, and you don't need to look at those. It's way easier just looking at fragmentation, page density, and number of pages. So any questions, Mike?
Not right this second. It looks like one's coming in, but I'll bring it up when they're done typing.
Okay, cool. So this is a demo that's going to create a bunch of fragmentation. And it takes some time to run. It might take longer on some of your systems. So I've already run it. And what this code does is it creates a database called GUID test, and it creates 2 tables, one called bad key table and one called better key table. Okay, very descriptive. And so you can see that they have exactly the same schema, except bad key tables C1, on which there is a clustered index, has a random GUID. Better key table C1, on which there's a clustered index, is a sequential GUID. And this was added in 2005 to give you large sequential runs of GUIDs, which obviously causes less fragmentation. And then what I did was I've got a few other columns and a non-clustered index on the date time column, and I inserted 250,000 rows into each of them. Right? And we can look at the fragmentation. So that already ran. Now, I can look at the fragmentation and show you the results of the DMVs, and we're going to look at that. But what I also want to do is show you how quickly the various DMV options run. So this little piece of code here is just me turning on XP command shell so I can go out and delete any old extended events files, and then turning off XP command shell again. So what I'm going to do is create a little extended event session, and this is using the old syntax for extended events that works all the way back to 2008. And I'm going to look at the SQL statement completed event. It's going to capture things like how many reads did it have to do, how long did it take, and I'm also going to capture what was it actually doing. So I'm going to go ahead and set up that little event session. And then we're going to run the 3 modes of the DMV. Detailed. Oh, by the way, at the end of this script, I forgot to say, it drops everything out of memory. Okay. So it's going to run detailed, drop stuff out of memory, sample, drop stuff out of memory, limited, drop stuff out of memory. Okay, so it's gone ahead and done that. Very quick look at the results of the DMV. We'll look at the, let's see, this is the detailed mode up here. And you can see it gives you the object ID and the index ID. It doesn't give you the names. And when I was building this DMV, I wanted to put the names in, but I lost that fight. So to get the names, you're going to have to cross-apply with sys.indexes to get the index name and the object name. And you have to use cross-apply because this is a table valued function, essentially. The partition number, I didn't create any partitioning, but everything is partitioned as far as SQL Server is concerned. If you didn't create any partitioning, it has 1 partition. Then the detailed mode is going to give you 1 row for each level in the index, and then information about them. So you get the average fragmentation to like 10 decimal places, and then we get the page count and the page density. Okay. So in these pages, the average page has 33% empty space. Right. Now, if we look at the limited mode down at the bottom here, excuse me, I just need to take a little drink of water and cough. So I'll just quickly. It's quite dry. Okay, that's better. So we look at the limited mode, we can see that, whoops. We look at the limited mode here, we can see that it gives us the average fragmentation in percent, it gives us the page count, but we don't get the page space used. We don't get the page density because it's not reading the leaf level pages. There's a whole bunch more stuff that the DMV gives you, but it isn't pertinent to our discussion on fragmentation here. Now, what I really wanted to show you was how expensive the various different methods were. There's 2 sets of XQuery code here, 1 to run if you're on 2012 or higher, and 1 to run if you're on 2008 or 2008 R2. And this is going to pull out the information from our extended event session. And what we can see here is how long each one took. So we can see that the limited one, 56 milliseconds, up to the detailed one, okay, almost 4 or 5 times more of that. And now scale this up. This is a very small index. Scale this up to maybe a clustered index with 100 million pages and 4 or 5 times more expensive and having to read all those pages. Okay, difference in physical reads here. And this is why you want to try and use the limited mode if you can, because it does a lot less work and it takes a lot less time. Okay. Now, if we go and look down at the bottom, I've got a little script which is going to actually run the detailed mode because I want to look at the page density and just pull out a few of the bits of information and kind of prettify the output and give us names. So we can see here that our bad key table clustered index had almost 100% fragmentation compared to our better key index that had less than 1% fragmentation. But look at, less than 1% fragmentation. But look at this, our bad key table non-clustered index, 30% fragmentation compared to less than 1% for our non-clustered index over here. And this is showing you how a random cluster key can also affect the fragmentation of non-clustered indexes. If we go back and look at the schema here, so my non-clustered index is on a date-time column, okay, and it is non-unique by default because I didn't say unique. And what's happened here is it took 40 seconds for my laptop to insert 250,000 rows, right? So it's able to insert thousands of rows every second, right? The minimum time period that a date time column can resolve is 3.3 milliseconds. So if I can insert a bunch of records every 3.3 milliseconds, which my laptop can, that means that they're all going to have the same C2 value. And in a non-unique, non-clustered index, under the covers, the actual keys used for this non-unique, non-clustered index will be C2, essentially, comma, cluster key, because a cluster key index has to be unique. And so for all the values of C2 that are the same, the insert point into that range of values becomes set by the next most key, which is C1. And in this case, that's random. So I'm having fragmentation because my part of my non-cluster key that's determining insert spots is random. If I made this a small date time, I'd have even more fragmentation in the non-unique, non-clustered index here. If I made it, say, a date time 2, most of that fragmentation would go away because it's resolving an awful lot smaller of a time tick. Maybe I think it's 100 nanoseconds or something. So very interesting that a random cluster key can also have a knock-on effect in terms of fragmentation in non-unique, non-clustered indexes in some circumstances. So we'll leave that there, and we'll do a few more slides, and we'll come back and we'll remove the fragmentation. So let's say you've got fragmentation. You've got two realistic choices to remove it. You've got a rebuild or a reorganize. It's also possible to do it using a create index with the drop existing equals on clause, but you have to specify the entire index, create index statement to do that. So if you're just going to do a rebuild, just do a rebuild. Okay? You'd only use create index with drop existing if you wanted to change something about the index, like changing partitioning, move it, or something like that. You could, as I've said several times, choose not to do anything about fragmentation for that particular index. Okay? If the index isn't suffering, or the workload using that index is not suffering because of fragmentation, leave it alone. Right? And you don't have to go and rebuild all your indexes every single day. Right? You might find that if you're using an availability group, a synchronous mirror or a synchronous availability group, that you can't do a rebuild because you have to use the full recovery model in those two situations. And so a full recovery model rebuild is essentially going to log the entire index. And so you might have to do a reorganize, and where you can do a set of reorganizes every day. If you are in that case, then go to Google or Bing and look up Paul Randall staggered index maintenance. And you'll see several articles where I've written about how to use a reorganize in that situation with a little chunk of reorganizing done every day. And so you kind of essentially remove fragmentation on a large index over a period of time. So a couple of slides just comparing and contrasting rebuild versus reorganize. A rebuild can run in parallel. You can control how many CPUs it uses as well. It's going to rebuild index stats with the equivalent of a full scan, okay? Unless you've got a partitioned index where it'll do sampling. A reorganize, by comparison, is always single-threaded because of the way the algorithm works, and it never touches statistics. Right? You can rebuild or reorganize a single partition. You weren't able to online rebuild until 2014. You've always been able to online reorganize because that was the whole point. Reorganize is based on the old DBCC index defrag that I wrote for SQL Server 2000. And the whole point of that was to be an online interruptible low space requirement alternative to the old DBCC DB reindex. Right? So a rebuild you can do online, right? You can rebuild a clustered index online from 2012 onwards if it has a lob column in it. So a non-legacy lob column would be var binary max, varchar max, and varchar max, or XML. Before 2012, you couldn't rebuild online your clustered index if there was one of those columns in the table. Okay, from 2012 onwards, you can. However, if you have a table that has a text and text or image column, you cannot do online index operations on the clustered index of that table. No effect on the non-clustered indexes, but you can't do it on the clustered index. 2017 onwards, you're able to actually pause and resume an online index rebuild, which is pretty cool. So you can start an online rebuild running and say it's resumable, and then you run another command that says pause it. And then maybe that's the end of your maintenance window. So you come back in the next night and you say go, and it does a little bit more until the end of your maintenance window. So this is another thing you could do to do staggered index maintenance. Okay. Now, a rebuild can be minimally logged if you do it in the simple or bulk logged recovery models. Okay. But that's not going to have any effect on the size of your log backup, just the amount of log that's written out. The log backup still has to back up essentially the whole of the new index. Okay. A reorganize is always fully logged, but as we're going to see, it shouldn't generate as much transaction log. Okay. An index rebuild is always going to build you a brand new complete index, no matter how much fragmentation there is. An index reorganize is only going to take care of any fragmentation that exists. So if you have a heavily fragmented index, it's better off to do a rebuild. If you have a lightly fragmented index, you're better off doing a reorganize. And I've got some numbers in terms of thresholds to tell you about coming up. You can also use sort in tempdb for an index rebuild. So if the index rebuild requires a sort, you can get it done in tempdb, which reduces a bunch of logging that's done. So especially if you have an availability group or a mirror, reducing the amount of logging means reducing the amount of stuff that has to be sent across the wire by doing sort in tempdb. So that's a good thing. Right? Now the cons, it's an atomic operation. If you interrupt it when it's 99% done, it rolls the entire thing back. It's all or nothing. A reorganize is built to be interruptible. The most it's going to do is roll back one small part of the operation. Right? A rebuild also has to build a brand new index, and it has to finish building the index before it can drop the old one. So that means you need a bunch of extra space, at least probably the size of your index. An index reorganize uses one 8K page, so it's very low space requirement. A rebuild also takes big locks. What I mean by big locks? Big blocking locks. So if you're doing an offline rebuild, which is the default, it takes what's called a schema modification lock on the table. The entire table, even if you're rebuilding offline a non-clustered index, is unavailable for reads or writes. There are still some locks that are taken for online rebuilds, and I'll get to that. I've got a slide that shows how online rebuild works. So it's not completely online, right? But the phrase almost online index operations is not a very good marketing term, which is why the marketing for SQL Server 2005, where we put in online operations, called them online operations, but there are actually still points where they can cause blocking. So I've already mentioned most of what's on this slide about reorganize. It's always online, so it doesn't take big blocking locks. It requires a table intent exclusive lock. So all it's going to block are operations trying to take either a table exclusive lock or a table share lock or a table schema modification lock. So it doesn't block things. Right? It's interruptible. It has some progress reporting. Most of the DBCC commands have progress reporting in the % column of DMExec requests. It also, if you have off-row storage for lob text values, it's going to compact that. Okay? They broke it after I left, and every version of SQL Server up until I think 2016, it was broken in for a while, but it's fixed also in every version of SQL Server. And there's a blog post there, link, that has the builds that you need to be running on for the lob storage compaction to be fixed. Okay. So for a rebuild, it's going to be better to use that if you have a lot of fragmentation. For a reorganize, it's going to get bogged down if there's lots of fragmentation and take probably longer than a rebuild. So you're going to use that when you've got a lightly fragmented index. So you've got comparison points between a repair and a rebuild. Sorry, not a repair, a reorganize and a rebuild. how much space you have, how much log is being generated, how much speed you want it to have, whether it needs to be online or not, whether you need it to be interruptible or not. And one or more of these things may force you to choose a reorganize instead of a rebuild. And that's perfectly fine. So when do you rebuild versus defrag or reorganize? And there are numbers that I came up with. These numbers I invented when I was at Microsoft because people wanted guidance. I didn't just pull them out of thin air. I was talking to the customer advisory team, product support, working with clients. And these numbers I actually came up with: less than 10% do nothing, 10% to 30% do a reorganize, 30% and higher do a rebuild. And this is for logical fragmentation. And now you'll see that Books Online says 5% instead of 10%. But basically, these numbers are what I came up with, and you'll see this is what Management Studio uses. This is what Ola Hallengren scripts use, and many people use these numbers as well. But you might find that for some of your indexes, these numbers aren't the best numbers, and so your mileage may vary. Now, I haven't done this for quite a few years now, if you desperately want to pay me to write an index maintenance kind of scheme for you, I'll say no, go and look at Ola's code, because there's a guy called Ola Hallengren, he's an MVP out of Denmark, I believe, who's written Ola's maintenance solution, database maintenance solution, which does index fragmentation, it does statistics, it does backups and check DBs as well. And it's completely free, and he maintains it, and it's used by hundreds of thousands of people all across the world. So I'd rather that you went and downloaded that and used his code, or at least take his code and change it if you want. And what that basically does is if I was going to do it for you, I would have a list of indexes that I know have fragmentation issues. And I would run the index physical stats DMV just for those indexes. There's no point running it on the entire database if there's only 10 indexes that you care about. For each of those indexes, I'd have thresholds to say whether to do nothing, to reorganize or rebuild, and do those based on the fragmentation that exists. Keep a log of what was done, so you can look back and see how things change. And then something else that I used to do was if I saw that an index needed to be rebuilt 5 times in a row when the code ran, I'd programmatically lower the fill factor down to something like 50% in chunks of 5% at a time. And that's what I call pause method. And you'll find that there's other people that have written index fragmentation code as well, but Ola's is, I'd say, the gold standard. And that's basically what that does. So before we go and look at removing fragmentation, which is only like a 30-second demo, how does an online index operation work? It's basically, you want a new index. So let's say we've got this fragmented index here on the left. What it's going to do is it has to take a shared table lock, first of all. And while it's holding that shared table lock, it creates a new empty index that is called being in build. It recompiles any query plans that are touching the old index so that any inserts into the old index will also insert into the new index. It creates a separate version store in TempDB that only exists when online operations are running. And it does a version scan, so a point-in-time version scan on the old index. It doesn't turn on snapshot isolation. It uses that mechanism under the covers to see a point-in-time view of that old index. Then it drops the share lock, and it's holding a intent share lock, which is a very lightweight lock, while the version scan is running. At the end of the operation, it has to take a schema modification lock because it's going to force all plans to recompile. Basically, it bumps the major schema version number of the table. So when the schema mod lock is held, it drops the old index, and now we've got the new index. It essentially swaps the index pages under the covers, so the index ID and name and everything stay the same. Now that share lock and that schema modification lock can cause blocking. There's a way that you can work around that from 2014 onwards. You can say that you want your online index operation to wait at low priority. And you say, I want to wait at low priority for a number of minutes. And after a number of minutes, if I'm still blocked waiting for that lock, tell it what to do. So you can either say do nothing, which is kind of pointless, or excuse me a minute. I'll just mute myself. I haven't done any lecturing this year yet, so my voice gets a bit croaky if I just speak for an hour. So you can say wait at low priority, and then after a certain number of minutes, do nothing, which, as I said, is pointless, or stop waiting for the online index operation and kill that operation, or you can say kill everybody that's blocking the online index operation. So it's kind of interesting how you can do that, and that also works for online partition switching as well. So quickly, a quick demo to look at the removing fragmentation, and then a couple more slides and we shall be done. So we've got this fragmentation here. We have a number of different ways that we can remove the fragmentation. So first off, let's look at the clustered index. So we'll go ahead and do an online rebuild of the clustered index and set the fill factor at the same time. You can only set the fill factor using a rebuild. You can't set it using a reorganize. So we go ahead and do that rebuild, and we'll look at our fragmentation. It goes from 99% down to, why did it not change? Did I run this? How very strange. Why did it not change it? What am I doing wrong? Oh, because I'm in the wrong database. That's why. And I must have had that table in the master database. All right, let's try that again. Okay. That's better. Okay, so 99% down to 0.3%. And we can see that we've got our page density there set at 70, so that's good. Now, if we look at this, I specified online equals on. This would have failed, okay, on 2008 and 2008 R2, and in fact on 2005. And it would have said, you can't do an online index operation because your table has a lob column in it. If we go back to the schema, you can see that I put in a 1 byte varchar max. And on 2008, 2008 R2, that will stop online index operations on the clustered index. Okay. Now, let's look at reorganizing the non-clustered index there with 30% fragmentation. And we see it drops down to 1.4%, but we can't set the fill factor. To set the fill factor, we have to do a rebuild. So if we do the rebuild, now we've got the fill factor set as well for the non-clustered index. And we can see we've got a tiny bit better fragmentation from doing the rebuild versus the reorganize. And you usually find that's the case, where a reorganize can get it down to low single digits, and a rebuild can usually get it down a little bit lower than a reorganize. But 1%, 1.4% versus 1.5%, I don't care about the difference there. So very simple, just showing the rebuild versus reorganize. I told you this demo was very short. So one other thing you should consider are, do you have a bunch of extra indexes? Do you have non-clustered indexes that aren't being used at all? If they're not being used at all, and they're not enforcing a uniqueness constraint, then they are candidates for being dropped, because if they're not being used, they are being maintained in real time by inserts, updates, and deletes on the table. And you might also be defragging them as well as part of your index maintenance. So look for some blog posts around DMDB index usage stats to show you how you can find out whether your index is being used. So to summarize then, you are going to have fragmentation in your databases. That doesn't mean that you have to do anything about it, but you at least have to look to see whether that fragmentation is causing you a problem. So you find the various indexes that have lots of fragmentation, and you measure your workload performance, and then maybe you're looking at how many page reads are being driven by normal workload. Remove that fragmentation and see if the workload gets faster. If that's the case and you want that speed increase to stay there, you're going to have to do something about fragmentation. And usually that means setting fill factors and doing periodic index maintenance. And it's that simple. But just don't follow the advice you might see on the internet of just not caring about fragmentation. You at least have to care once. Some resources for you. There's a lot of stuff about fragmentation on my blog. There's a Pluralsight course I recorded that's longer than the session. It has a bunch more interesting little demos and some more depth to it. Then you can get that. And if you, as I said, if you don't have Pluralsight, you want to give that a try, shoot me an email and I'll send you a completely no strings attached code to be able to try that. There's another link to Ola's scripts for automating index maintenance. There's no good white paper on this, unfortunately. There's a white paper that I helped write for SQL Server 2000 that they never updated. All the concepts are the same, but it talks about the old commands. If you are an insomniac and you have problems sleeping at night, the white paper down at the bottom will help you out. So this is it's a very dry white paper. It's very interesting, but it is very dry about how online index operations work in great depth. Okay, so that's the resources that I've got for you. And with that, we are done. So, Mike, are there any last questions before we all drop off?
That was really good, Paul. I have a couple comments on your summary slide that, you know, in today's presentation, I knew this, but it hit me very, very strongly today on the impact on log backup, log shipping, mirroring, scanning, AG, and how to keep track of that. I've seen that with a few of our clients, and I didn't realize it was probably driven by fragmentation.
Lots of extra page splits happening. Yep. And again, that's because most people just think about fragmentation slows down scans without thinking about how did we get fragmented in the first place.
Yeah, and the other one is the second one, right? They're paying gobs of money for SSDs, and let's just store a lot of, you know, wasted space out there.
Yep. Exactly. Yep. Cool.
So that is really good. I mean, you know, we heavily use Ola, which I think, as you recommended, right? And so, you know, and it has a nice fragmentation there. So I do want to spend a bit more time on that.
Cool.
Yep, that was really good. Really good. I like that.
Okay, I'm glad you enjoyed it.
Very. So, and with that, I want to just formally thank you very much for, you know, coming online and taking, you know, an hour and a half out of your time and do this. It was really great. I appreciate the support you've given the group, and great to hear your voice.
You're very welcome.
All right. Thank you, sir.
Okay, I'll send you the materials right now. Take care, everybody.
Right. Appreciate it. Bye.
Bye-bye now.